All right, welcome back, everybody. This is part two. So the activity, use the following workbank below to and to the right to fill in the 5 boxes in the table below. So pretty much what I want you guys to do is put a check mark on the ones that you think are the 2 types of discontinuities. All right, so the 2 types of discontinuities would be the non-removable and the removable discontinuity. And then what do you think would be the graphical description for the non-removable discontinuity? So again, check the boxes. So yeah, in this case is when we have a jump. And the other non-removable discontinuity is when we have an asymptote. All right. And then finally, what do you think would be the removable discontinuity? All right. So in this case, it's when we have a hole in the function. All right. Using this information, we can pretty much determine, right, on the following question, which type of discontinuities we can use. So if we look at the graph above of f of x, determine all x values where f of x is not continuous and classify each removable or non-removable. So what we want to do first is find the x values and where it's non-removable. Where it's just discontinuous. So for sure, if we start on the left side, we'll notice that it starts off at x equals -1, right? So when x equals -1, there is something that's happening right there. The next one is when we see right there at x equals 3, all right? So what happens there too as well? X equals +1, not 3. The next one would be x equals 3, right? So this one's right there at x equals 3. And then the last value where you can see there's a discontinuity, right? We have to pick up our pencil, is right there at x equals 5. All right. So now that we know this, we can pretty much determine which types of discontinuities we have. So for sure, if you look at the first at x equals -1, we have a jump in the graph, right? And then at x equals +1, we have a vertical asymptote. So these two are considered the non-removable discontinuities. And then for x equals 3 and x equals 5, right? So again, let's look at what happens right there. So if you notice, they're pretty much the limit exists, right? As we approach the same value from both sides, but there is a little gap in the graph right there. So these would be the removable discontinuities because they're just pretty much holes in the graph. All right. And the way I like to think about these, pretty much if like the non-removable ones is when the limit doesn't exist. And then removable discontinuities is when pretty much we can see that there is a limit, right, as we're approaching it from both sides. But the function may not be defined there, all right? And then example 2, consider g of x equals x squared plus 3x minus 40. List the x values where g of x is not continuous and classify each type of discontinuity, and then write the intervals over which the function g of x is continuous. So again, pretty much the first thing is we'll want to do is look at the function. We have g of x is equal to x squared plus 3x minus 40, and then over x squared minus 3x minus 10. Now remember, we can't just cancel things out on top of them like that just randomly. We have to make sure that everything is already multiplying on top of the bottom, right? So we want to factor this to see what's going down, right? So let's factor the top first. So that's going to be x plus 8 times x minus 5. And then if we factor the denominator, we're going to get x squared. So that's going to be x plus 2 times x minus 5. And again, these two are divided out, right? And then this takes us to x plus 8 over x plus 2. All right. So pretty much the things that we can divide out are what we consider the removable discontinuity. All right. So if you're able to remove it, right, because if you notice here, like if I was looking for the limit, for example, I can see it's approaching a value as x approaches 5, but the function is not defined there, right, because it is indeterminate. So this would be like having a hole. So when you divide these two out, it's like having a hole in your function. All right. So these are considered the removable discontinuities. Removable at x equals 5. And that's again because I can divide things out, right, to get rid of it. And then the non-removable would be when for sure we have an undefined. And the only place we have an undefined is when x is equal to negative 2, right? If we plug in x equals negative 2, then we're going to get 8 negative 2 minus 8, plus 8, negative 2 plus 8, and then divided by 0, right? So again, that would be considered undefined. So therefore, we want to say that's the non-removable discontinuity because we would have an asymptote there. So the non-removable is at x equals negative 2, right? And then when they say they want us to write the interval, so we want to make sure that we also write the intervals over widths continuous. If we're talking about continuity, we can use what they say open intervals. So that means when we're using the parentheses, right? So that's open intervals. And then that's, again, we don't include the endpoints. And then pretty much for the closed intervals, right, is when you guys use the closed brackets. So here we're looking at the first interval that we see is that we're coming in from negative infinity. What I suggest is that you guys look at the graph so you can determine the intervals. We're going from negative infinity to negative 2. And then the union, right, after that, we jump from negative 2 to positive 5 to the next discontinuity. And then from there, we're going to go on to our next one, which is 5 to positive infinity. So again, it's a lot easier if you guys look at the graph, and I suggest you plot this on Desmos, right, to determine the intervals, right?